All right, so let's continue with the second part of this talk, bifurcating minimal surfaces with symmetries. As a reminder, this is a talk in 4 parts. This is part 2, basic tools from bifurcation theory. So bifurcation as a term, as a mathematical term here, was coined by Poincaré in 1885. And in this very beautiful paper, which I highly recommend reading, it's surprisingly readable, perhaps. And it's described as a topological change in the structure of the dynamical system when a parameter crosses a bifurcation value. So for us in this talk, I want to focus on the following type of problem. Let's pretend we have an equation we're interested in solving. Maybe the equation is of the form f of a s equal to 0. A is a parameter. So maybe write a little bigger. And s here is the variable, as in the main variable that we're controlling. And we're interested in finding solutions of this equation, pairs a comma s, such that that's equal to 0. And suppose we have a trivial family of solutions. So throughout the talk, these are always painted red. And we can assume, for example, that they're set at 0. So s equal to 0 would always solve this for all values of a, all values of the parameter. So one possibility to try to produce non-trivial solutions, namely to find solutions other than just 0, is to study how stable or unstable 0 is as a solution to this equation as we vary the parameter a. So this is what I mean by try to deform the trivial solution 0 until they become unstable. And then you might find some non-trivial solutions. Okay, so here's a very silly and very simple example. I apologize perhaps for the simplicity, but I think it captures the point despite being so elementary. Suppose that our function for this purpose is this function here, right? This polynomial. Of course, we know how to solve, we know how to find all the solutions to the equation s cubed equal to as, but let's pretend for a second that, you see s equal to 0 as a solution, and we plot that here as, 0 is a solution for all values of a. And we want to find, and we want to know if more solutions appear somewhere along the way or not. Okay. So in this case, since it's so simple, we can just solve it by hand, right? If s is non-zero, I can just divide by s, and s squared is equal to a. So if a is positive, then I can set s to be plus minus the square root of a, right? So then we find 3 solutions for positive values of a. So let me put here a curve. Let me try to draw a little bit better. So here we have, let's say, square root of s and minus square root of s. So for all positive values of a, there's these 3 solutions, right? 0 plus the square root of a and minus the square root of a. And I just realized I wrote square root of s. What I mean is square root of a. Okay. So in general, if this was a more complicated problem, what's so special about this point here, about this value of a, namely 0, where these other solutions show up, right? So the point here is that if I linearize the equation, well, if you linearize this polynomial, just take a derivative in s, right? That's 3s squared minus a. If I linearize this and compute it at that special point, so the trivial solution, s equal to 0, then I find something which is, well, minus a. I find something that is 0 exactly at this point where the new solution showed up, right? So that's one information. The other relevant information is the mixed derivative, the mixed second derivative. And in this case, you can just take a derivative in a and you see this minus 1. So the relevant point here is that this number is not 0, okay? And this is a general fact. So as soon as you have a 0 here, as soon as the linearization is degenerate and the mixed derivative is not 0, then such a bifurcating branch of solutions will appear. That's the theorem of Crandall and Rabinowitz. So here's the statement. Suppose we have, of course, I'm omitting some technical things, but this applies in a very broad context, actually. Suppose we have a trivial family of solutions at 0 to the equation f(a), s equal to 0. And there's this value a star where these two things that I discussed before happen. The linearization is degenerate, and the second derivative, this mixed derivative, is non-zero. So here, I guess x is s. I didn't change the notation there. My apologies. So then there exists a neighborhood. The conclusion under these hypotheses that there exists a neighborhood U of our point a star comma 0, such that if I look at the solution set, so the inverse image of 0 intersected with this neighborhood, that has the trivial component, so these points that I'm writing in red, the points of the form a comma 0, well, of course, just the ones in U since I'm intersecting there, together with a curve. So let me maybe draw here a curve, B, where this blue curve, B, is what we call a bifurcating branch. Okay, so this is, assuming f is smooth, this is a smooth curve, and the proof is actually a very nice use of the implicit function theorem. All right, so this is the local bifurcation result, since it gives me a neighborhood here of that special point where this happens. And then the question is, what happens to this branch? Does it keep going, right? Can I go beyond this open neighborhood U? And that's ensured by this global bifurcation result, which has an extra hypothesis, and it goes like as follows. So since we're going to try to globalize the thing, let's imagine that the space of where S lives is an interval I. So I is an interval that contains 0. And here is denoted by this vertical interval, so with these endpoints. All right, then we can define a bifurcating branch more generally to be the connected component of the solution set, which stems from some point here along the trivial branch. Okay, so by the way, this red set, sometimes we call it the trivial branch, right? Okay, so the theorem of Rabinowitz says the following. If we add the hypothesis that the restriction to the 0 set of the projection onto the parameter, so the map that sends a comma s to a, if that restriction is a proper map, so meaning the inverse image of compact sets is compact, then there's a dichotomy. Every bifurcating branch that issues from some point here along the trivial branch, either it reconnects to the bifurcating branch, so maybe it goes back and closes up a circle like that. So either it reconnects to the trivial branch, or reattaches to the trivial branch, or it just goes on forever, or it's non-compact. So non-compact. So it doesn't just die there. It doesn't stop in the middle. It has to go on to infinity. So for example, here it could go on to infinity. It doesn't have to go asymptotically to the endpoint. It could go on to infinity like that, or it could go to the boundary here. Maybe it could do something like this as well. Okay. All right. So this is a very useful dichotomy that will play a very important role in the next couple of parts of the talk when we talk about minimal surfaces in ellipsoids. So to finish this part, I'll do some commercial break here. So these are two very nice books about bifurcation theory. If you want to read more about these two results I discussed and see the actual proofs, I highly recommend this book of Buffoni and Toland. It's developed on the framework of analytic functions, and it's a very good reference. This is a very comprehensive reference, this book of Kielhofer. It has a large number of results. It's a wealth of results there And it's a great reference for bifurcation theory as well. And some shameless self-advertising. Together with my collaborator, Paolo Piccioni, I wrote a survey on applications of bifurcation theory to geometric analysis beyond just minimal surfaces, which we're discussing here. So that appeared in the notices of the AMS a couple of years ago. And this is another survey more focused on the Yamabe problem. That again applies these ideas of bifurcation theory, namely these two results of Rabinowitz and Crandall-Rabinowitz to produce non-uniqueness of solutions to some geometric variational problems.